Welcome to Under the Microscope. This series is brought to you by the Real Scientists Nano team. Our goal is to provide a platform where scientists can communicate their work and interact with the public. With that in mind, every week we introduce you to a scientist working in the field of materials and nanoscience, who would be curating the RealSci_Nano Twitter account.
Hi everyone, today we have with us Joe Sharp, who is a research fellow in advanced characterization at the University of Sheffield in United Kingdom. Hi Joe, how are you doing?
Hi, I'm good, thanks. Sitting in the sunshine.
Send some sun here, please. All right, let's talk about your science. So, how did you end up in your current research field?
That's one of those questions that's really hard. Sort of like magnetically by accident. Not by accident, but like I just drifted, sort of. Well, let's start. So atoms when I was 12 at school from Mrs. Barnes in a science lesson, and I just sat there and looked at my hand and went, "Whoa!" And then I looked at the table and went, "Wow!" And then I've kind of been doing that ever since. Like that day I just walked around completely like, whoa, all day long. And like I kind of kept, like, every lesson after that was science carried on like that. It was kind of, I must have been a real pain in the bum for like English classes, because I was just looking out the window going, cool, at all the trees. But yeah, but that's okay. So sorry, Miss Owens, that I was a terrible English pupil. She's probably not going to hear this. So after that, I sort of gravitated towards science at every opportunity, because it's like, it was just so cool. So did that, went, yes, GCSEs, yes, A-levels, all that. And then I kind of ended up doing natural sciences at Cambridge, because like I didn't want to do all physics because chemistry was cool, and I didn't want to do all chemistry because physics was cool. So I sort of did natural sciences and went, I'll just do as much as possible for UV science. So I did. And then I sat in the physics lectures and went, I understand thing, because like I only had half a maths A level and everyone else had 2, and I was like, oh god, I don't understand anything. I was like, oh, maybe I actually suck too much to do this. So I almost quit, because I was like, I suck, I'm awful. But I didn't quit, because like, well, what else was I gonna do? Like, atoms are so cool, I have to just study them. I have to look at all this stuff. And I was like, well, I didn't have anywhere to actually go if I quit, so I was like, well, guess I'll just stay. So then, like, I didn't know at that point that I had a learning difficulty. I just thought I sucked, right? So I kind of figured out a way of like going to the lecture. I understood nothing, but I could write down what I saw, and then later I could go and like make that into pictures and stuff and understand it. So it took a lot of working around. But once I got it, like, I understood stuff, that was okay. It's like I had to learn, when I was learning to drive, I had to know how the engine worked. Otherwise it wouldn't work. And it's exactly like that. Like, I couldn't just learn it, I had to understand it. So once I understood it, like, I started getting really good marks in like the courseworky type bits, because like I understood what was going on, and it was like, oh, that was good. So the fourth was like a master's year that goes straight on from a degree, and I did a project, like your individual project was your big thing to show how. I did this new electron microscopy technique to get like 3D images of defects in crystals. And that was really hard. And my supervisor, actually, he only had that as a master's project, because he was like, if I put this as a PhD project, they might fail and it would ruin their PhD. So I'll put it as a master's project first. So we had a go, and it worked, and it was like, ooh, and I got a really good master's thesis. I got like a first for that master's project, and then got a 2-1 because I was really bad at exams, because I couldn't write very fast. So but I got enough marks to carry on and do a PhD. So I was like, oh well. So my supervisor was like, well, come and do a PhD, because that's what I wanted it to be. I'm like, okay. So I carried on and did a PhD in all this stuff, and did all sorts of fun things. And this is kind of where I started doing different materials, just trying stuff, what will work with different materials. So I just carried on, and it was kind of like I could do what I wanted to do, but my learning of how to do things on microscopes and like lab learning was really like I'd always been the person that just spills everything everywhere at school, and I still was, and I didn't understand what was going on, and it was terrible. So in the end, I took 4 years, then I ran out of money, and then I got a job and moved to Sheffield for this job. Then I got fired because I don't know, like probably internal company reasons or something like that. I don't know. So yeah, so then I had a summer without a job and actually finished writing my thesis and graduated. Yeah, I know, and applied for a lot of jobs and got a lot of rejections. But then I got a lot of interviews as well, which I wasn't really expecting, because I was applying for stuff like, I don't know, like Xray beams and proton accelerators and stuff, and it was like I got interviews for them. Okay, then, weird. So yeah, so then I finally got 3 offers, and I took the one which was like the one that I thought I'd be able to do best, basically. Like there was one where they hadn't got the microscope yet, but they were really nice, and there was one where it was for a year, but they were also really nice, and there was one where I already lived that was for 3 years, and I was like, yeah, I'll take that one because I hate moving house, and it sounds fun, and it was fun. It was great fun. So I kept going, and I turned out to actually be quite good at this. When I can, decide my own way of working and stuff, I'm like, oh, I don't suck much. So I sort of, and during this postdoc, I've kind of gone project to project. So like I drifted. So I started off with ceramics, and then I went towards like coatings and stuff, and then I've gone towards alloys, and then I'm sort of ended up doing aerospace alloys and additive manufacturing of aerospace alloys. So I'm kind of like a useful boat that just goes around different harbors when it's needed, but like it's quite cool. And I got a few years ago, I think when I was 34, I can't remember how long ago it was because that's how it works. I thought, well, hang on a minute, do I have a learning difficulty? Because I went to a session on how to support students with a learning difficulty, and I thought, well, hang on a minute, some of these sound like me. So I went to go and get screened for it, and it was like, oh, actually, like through the support service for students also has a staff bit. So, and I went through all the tests and stuff, and it's like, actually, you have dyspraxia, and apparently my verbal processing, everything else, I'm like pretty good. My verbal processing is in the lowest 1% of the population. It's like, no wonder I can't write essays. Wow, I know. It's like, goodness. So I've been like propping that up with everything else for my whole life and never knew. It's like, that explains a lot. So like that, then everything fell into place. Like I don't suck. I just operate differently to how the world the shape of the world. So I have to I'm like a motorbike in a world of cars. Like just mind the drain covers and you'll probably be okay.
Yeah.
Kind of.
Wow.
Yeah.
Wow. That is, wow. Okay. Wow, your journey has been so interesting. Wow. And I'm glad that you know now what you are. So it's not your fault. It's not, it's the world. That you just, you are wired differently. That's what it is about. It doesn't mean that you suck at stuff. It's just, you're just wired differently. Wow, that makes sense. That's wow. That's I'm happy for you.
Thank you.
That you have it figured out now. You have some answers.
Some.
And also your research. It sounds so cool. It's very typical to say. I'm putting it in quotes here. Typical for a scientist to do hopping. And we'll definitely talk about that at a later point.
Every day is a science lesson.
Every day is a science lesson, absolutely. So my next question is about, you already spoke about what your research is, what your current research is in the short podcast. So how and where do you see your current research fitting in this big picture of materials or nanoscience?
Okay, at the moment, my research is mostly alloys and additive manufacturing, which is it's kind of like 3D printing, but that implies it's a little bit easy, and it's not. So that means in terms of alloys, you build something out of molten metal. So you either lay a layer of powder metal down, and then you melt it in a pattern with a laser, or you have your laser go around and you're blowing you're blowing metal powder in through little jets at the side, and then your laser catches it and melts it onto the thing you're building, which is really it's really, you look at it and think, how does that work? And then you're like, whoa, there's a thing coming out, it's working, it's cool. So yeah, so that's how you do it, but it's so different to how you normally build things out of metal, like forging and stuff. So the cooling rate's crazy fast, you wouldn't, it's mad, it's amazing. So the structure, the microstructure of your material, how all the things inside go, is really, sometimes it's just completely different to what you'd normally get. Sometimes it's a really teeny tiny version, because if your cooling rate's fast, you get tinier features because they just don't have that much time to grow.
Right.
And then you get extra bits, little bits where the laser beam's kind of gone past and done some melting, and then it comes past and does a bit of remelting, so you get little stripes and stuff in it as well. That's quite cool. So and a lot of these features, because they're nano sized, I sound like more Mindy there, because they're so tiny, you need sort of nano size characterization. So a lot of electron microscope time is used looking at these things at the moment.
Okay. Wow. Okay. Yeah, that is so cool.
Isn't it?
It's just, I need a moment to just be like, wow, just try to visualize it. I have all these things, all these techniques are happening at nano or micro level. That is just so cool.
And it's macro level when it's going. The laser is normal. It's a millimeter or 3 millimeters across the beam, but what you get coming out is just so little. It's amazing.
That's so cool. And it does sound to me that you are, clearly you are involved in a lot of interesting research projects, clearly, and have been doing some amazing, even your master project that you mentioned, that's also so cool. And this question is going to be difficult. I know that because I have been a scientist, but I'm going to try to ask you this question. If you have to pick one research project that you're most proud of, or the most fun or quirky one, I know it's difficult. Could you pick one and explain it to us in simple words in the section we call In Other Words?
Okay. So the thing I'm probably most proud of is my PhD, because I survived. But also that's really hard to explain in simple words. So I might just do that in the Twitter thing. I'm gonna do a different one here, which is the recent one that I'm very proud of that we did, because it just took so much effort and so much failing and getting it different. So I'm proud of all of them, really. So the most recent one that we're finishing and writing a paper right now. Come on, we're gonna get there. So yeah, buckle up, this is good. Okay. So when you make a metal by additive manufacturing, you get little pores of gas trapped in, just because of how it works. And so you get it sort of to get rid of the little pores, because the little pores can be a place where a crack will start if you're loading it in different ways. So you, to get rid of these pores, you get it quite warm. So 700 degrees is not quite warm, it's really hot, but in terms of metal, it's quite warm. And you put lots of pressure on it, and it's supposed to make the pores close up. But then in a lot of alloys, especially titanium, actually once you've got, because that process will make your piece squash a bit, and it will be a different shape. So once you've got it to the right shape by doing that, then you need to heat treat it at a much higher temperature, 1200 degrees centigrade, for a few hours. That makes kind of the atoms diffuse about and makes the best, the structure you want to make the alloy stronger. The strongest is not the one you get from additive manufacturing, so it needs that heat treatment to make it change. But once you get it that hot, actually, sometimes some of the pores will grow back. They didn't go away, they just got really tiny, so you couldn't see them on the methods you were using to check if you'd done it yet. So they grow back again, and it's well, that's really annoying. So we wanted to know how do you know where do they grow back? What shape do they grow back? What's in them and stuff. So we were trying to solve the what's in them problem, but it didn't work for that. But we solved the other problems by mistake, which is good. So we cover more bases than we intended to, just different ones. But that's okay. We have a plan for the other one. So if you're going to have pores, you have to figure out, like, well, can we live with them, or is this part like junk to this? So you do kind of X-ray tomography, like you do like tomography of a brain to do a brain scan. You do it on a much smaller bit of metal, with a lot more X-rays because it's not a brain. It's not going to get damaged. You do that on the little tiny bit of metal you made, to see where the pores are inside. But the resolution of that isn't that awesome. So you can say it's sort of 300 microns across. Well, it wasn't that big, the one we got, but you kind of assume they're round, which is a problem, because then from the size you calculate like what effect is this going to have on the amount of load it can take, or kind of the most important thing of pores is, like, if you have a load that kind of wibbles and wobbles, like if your part's in an engine and it's like the engine going round, and then sometimes it gets faster and sometimes it gets slower, like there's loads of different ways the load changes.
Right.
So that's the kind of load that a pore will start a fracture at. So you want to go, right, is this pore big enough to start a fracture in the load we're going to give it, or will it be okay? And then you put like a big old margin of error on it, because that's a good idea, you know.
Right.
So I should say, this isn't with the company that I work with. This is an academic project. So this wasn't going to go in a plane, but it's like kind of figuring out, like, how does this work in terms of when we would assess it to put it in a plane, would it work that way, kind of thing.
Right.
So yeah. So on these X-ray, like 3D scans of these bits of metal that we got, we looked at them and we're like, well, that one looks a bit hexagony, actually. Perhaps we should figure out whether it's actually round or not. Was one of the other, like, back burner things we had, as well as what's in it. Because, like, if it's got pointy corners, and the person who discovered about pointy corners was called Constance Tipper, and everyone should Google her because she was awesome, and no one ever talks about her in like material science lectures, but actually she was great. She founded so much stuff in like the 1920s. Anyway, digression. My lectures are brilliant like this, like I never get to the point. Okay.
That's fine. You can tweet about her. Definitely tweet about her.
I will. Lots. So yeah, so a pointy corner is more likely because it's pointy, basically, like the stress is more concentrated at the pointy bit. Yeah. So a pointy corner is quite a dangerous thing for starting a crack. So we're like, oh, actually, have we got loads of pointy corners? Because that would make it a lot worse than if it was round. So we did that. And so on our 3D X-ray scan, like, I got the X-ray scan and went, right, okay, let's put a mark where some of the pores are quite close to the surface and dig it up and slice it. And then measure, like, what the crystals are like round it, like what way round all the grains are around this pore,
right,
and stuff, and figure out some other stuff. And maybe when we get to the bit where we open it up, maybe we can catch the gas that comes out and see what it was, kind of thing.
Right.
Yeah. So we did that, and we missed the pore. Which is really annoying, and this is why I'm proud of it, because we failed so abysmally and then we did it right afterwards, and I was like, damn. So we spent all weekend on the mic. Well, first of all, I tried to dig it with I tried to get it out with an ion beam machine, which wasn't powerful enough, and it just took ages. And I was like, right, okay, let's quit doing this and ask the guy in Manchester with the really fast machine to help, and he can do it much better. So I did all this stuff, gave it to him. He spent all weekend on this machine, and there wasn't the pore. Because we missed it. So we went right back again. Okay, take another 3D scan with the hole in it that we dug to miss the pore. Find a pore that's another one that's closer to the surface, right? And then dig a little grid of marks so that we can navigate by the grid. Because that's how maps work, Einstein. And then put it back in and 3D scan that and get the 3D model and go, right, where do we need to dig the trench and pull out the block and then section it to actually get the pore? So I was like, right. And everyone was going, no, that was really expensive. Don't do it again. I'm like, no, it's going to cost a fraction of that now because we're going to do it right this time. And they were like, okay, just this once. I don't believe you. Not say everyone, like a couple of people. Everyone's not that mean.
Right.
So this time, we had this grid. It was just on the edge of the grid, which was like, oh, Jesus. Okay, we'll get there. So we went in to where this pool was, gave it to the dude in Manchester and said, dig there. And he was like, yes, okay. Set this up to work over the weekend. Double checked when he lifted the block out where the pool was supposed to be inside. He X-rayed that to make sure it was there first, because it was like, right. I am not spending a weekend doing this for nothing. So, did all the slicing and dicing and measuring. The data set, you have all the orientations for the different grains around the pore, and it is there in the middle, and it is beautiful, and it's not round. It's so cool. So the data, after all this faff and all this getting it wrong, looking like a pillock, actually it's there and it's done and it's beautiful, and we've got so much information out of that data set. It's amazing. Like where the pointy bits are, like where the pointy corners are and why they're there. You can see it from the data, because you can index what all the crystal faces are, and you know where the defects want to be on those crystal faces. So you can figure out like how it works, like how it's gone pointy kind of from where it was, and it's like, whoa. So now we know it's pointy. We know how pointy it is. Pardon me. We know why it wants to get that way. We have an idea for how to make it less pointy. Maybe that might work in a future thing. So that's quite cool. But just that it was so beautiful and right there in the middle. And we know there were lots of other little ones around it that we couldn't see before. But we totally missed when the gas came out, because the gas came out and then we did a scan of what the elements were, and it was like, well, it's gone now. We're going to do that another way. That's fine. We've got a plan for that one. It was like a long stretch for that one to start with. When we got the data set, I was in a meeting and I just went, yes! And everyone went, do you have something to say? I was like, I'll tell you later and you'll do the same noise. Yeah. And he did. My boss was like, whoa. So yeah,
it is quite wow. I can understand why you picked this as the one that you are like really proud of, the recent proud of one. Let's go with that, because it does sound so cool.
It was very cool.
Oh my God, that's and it's the way you explained it, the story behind it, basically. Like it didn't work the first time, probably didn't work the second time, but then you learned from that. You learned from why it didn't work, you made it better, and then it finally worked. That is so cool. I can't wait to read that paper. I can't wait to see those pictures and read all the theories and all. Wow, that's
nearly out. We're just doing a bit of calculating, and then it'll come out. Okay. Then it has to go through review, but we'll just forget about that bit of pain, the reviewing bit of pain, until it's out.
It's going to be out soon. Absolutely.
It'll get there.
Super. That sounds fantastic. So Joe, let's get out of the lab a bit and go towards the other parts of academic researcher, which is teaching. So do you want to talk a bit about, or tell us about the courses you teach?
Oh, wow. So I'm not like a permanent teaching person. Okay. I have covered some lectures for my previous boss when he was off doing well, he was supposed to be on sabbatical, but he ended up being roped into doing something else. And then he took an actual year of sabbatical. So I got to teach his course for 2 years, which was great fun. And that was, it was like a bit of a bigger course. And my bit was microstructure of alloys or something like that. Phases. I can't remember the title of it now. I think it was microstructure of alloys. That's really bad that I can't remember what it was called. I remember what was in the slides, but not what the title was. That's so bad. Anyway, my students know. They're probably gonna like see me and go, Jesus, her. But yeah, so that was all like, it was kind of going through the different alloy systems that are really important and going, well, this is what phases there are, like what kind of crystal structures it can be, and this is how you get to them, and this is what they're for, and this is how like you predict what's going to happen and stuff. And there was a little bit of like theory of like, okay, well, what does it mean? What's a precipitate for? What do dislocations do when they see different things? And it's a lovely course to teach, because it's so instantly like, here's this, it does that, ta-da, kind of thing, all the way through, and it's great. Okay. So yeah, but I think I've given that back to my old boss now. I think so. Yeah. But
Okay.
that was a fun experience.
Okay. Yeah, it does sound like fun. It does sound like a lot of fun. So let's go back to your research experience as a whole, as a scientist, and I hope your research experience has been wonderful so far, and will continue to be wonderful. Okay, wonderful is a strong word. Fun. Let's go with fun.
Well, it's going to be fun. It just probably will be terrifying too.
Yeah, absolutely, absolutely. So, if you had three wishes to make it less terrifying or make it more fun, what would you ask for? And I'm not promising anything here.
Oh, of course not. Oh my God, a permanent job. Then I could like everyone wants this, right? Just knowing that I'm gonna have a job, like not beyond the next 6 months, like in the future. And then I could like know, okay, I'll buy a house there and I'll make it nice. And this is gonna sound really, really like stupid, but a dishwasher. And all like then I could do adaptations to make it so the rest of my life doesn't wear me out, and I could just have more energy for actually doing the research, and it would just be such a change. And if you have a permanent job, you can you can apply for funding from places and go, yes, I'm going to have a contract for 3 years, so please give me money for 3 years. But at the moment, when I'm helping other people apply for funding, I'm like, well, we can put you on as a named researcher, but if they can't afford to pay the whole of my contract, then I might not be there, so it's a bit tricky. So I mean, I've got to sort this stuff out and apply for stuff, and it'll all work out somehow. It's just at the moment, I'm like, I'd love to know how. Like, the how could be a lot easier. That would be nice. In fact, just having a field where you can employ people for a long time it would just work so much better. Generally, I mean, put me in charge of all the science funding. Yeah, that'll work. Maybe, who knows? But yeah, I can whine about that for hours. So
Okay. Okay, so the first wish is
that was the first one.
Okay, all right.
The second one is like, this is a bit like niche and it might be a bit petty. I'm sorry. The idea that if someone's good at something, you can identify that they're good at something because they do it really fast all the time and they have a meteoric rise in how good they are, and they publish loads of papers in 3 years on the one subject, and they become the person for that subject. It's like, those people who can do that are awesome, and I'm glad they can do that, and I'll be happy to help them do that. But like, you also need people who don't do that. Like, you can't have one type of person to cover everything. Like, you'll miss so much stuff. And like, there needs to be a bit more room for funding people who either can't or just don't work like that. Like, not everyone's a stir fry where you get it really hot and the results are like, boom, brilliant. Some people are a casserole and they have to just process for a while. And like, it's a different kind of thing, and it's not a worse kind of thing, and there needs to be room for everyone, not just the rising star kind of thing. And it's also the rising star model is very much like, okay, that works if you don't have kids to bring. Well, I don't have kids to bring up, but anyway, that works if you don't have kids to look after and all the other stuff that pulls on your time, and it works if you can concentrate. And if your life isn't like that, like if there's a lot more demands on you, like, it's so hard to fit into that model. And maybe we need to stop making all the holes square. So some pegs are round. It's fine. Yeah. Sort of. And number 3, everyone's gonna yell at me now. I'm gonna regret saying this. Like,
no, all good. Go for it.
Honestly, on my wish list, when I ask people something, I'd like them to stop explaining to me how to do the rest of the thing, because I already know. Like, especially like mansplaining. It's 2020. Like, I know basic science. Most men understand that I know basic science, and we can just collaborate on a project. But every now and again, you come across someone who just assumes you're stupid, and it drives me absolutely crazy. So if they could just stop and be like the other men who are just reasonable, normal human beings, that would be great, please. It's just tiring.
Yeah, I can understand. Yeah, all 3 wishes of yours, especially the second one, that's actually I like the way you put it, that there should be room for everyone and not just the Yeah. There should be room for everyone. You're absolutely right. I like the way you phrased it. This is really, really important. Also, the third one. I mean, I can't believe this is still part of the wish list.
Yeah,
Stop the mansplaining, people.
yeah,
Stop it. I
yeah,
mean, no, just no. And I wish
yeah,
I could just do this and being like, okay, permanent contract done, place for everyone done, and no mansplaining. No man is ever gonna explain you
yeah,
stuff that you already know about. So I
yeah.
wish I could just do this.
Like women do it too occasionally, but it's like it's just so. Then you're like, oh, okay, that's interesting. But when a dude does it, like you're like, oh, this again? Kind of, it's so often.
Yeah,
It's just so tiring.
it is very tiring. Yeah. And then you have to hold yourself back from
Exactly.
reacting to it and being like, dude, um,
Yeah,
I know that's not what
yeah.
I asked. Tell me what I asked, and then we just get on with our lives. That's all I want. Um, yeah,
Ex-
well, let's hope that we are working towards it, and there are the number of men or number of humans explaining stuff to women
Who already know it
without asking for it
and
is going down.
wrote the thesis on it in some cases.
Yeah. Yeah, exactly. Yeah, I hope we are working towards achieving all of your three wishes, and the scientific community is working towards achieving all of your three wishes.
Mm.
And speaking of future, what are you most looking forward to in the next 3 months?
Oh my god. Well, in absence of saying a vaccine, because like that's not my that's not my job.
Yeah.
In terms of achievable things in the next 3 months, like I've got a lot of quite cool projects in the pipeline that with sort of like the teams on the projects are kind of starting to initiate them and figure out how they'll work and stuff. And they're going to be more academic, not so industrial, or like a little bit that they'll have a lower technology readiness level, which is like they're not going to go in a plane like now. So you can publish them, they're general enough and like fundamental enough that like it's not secret yet, kind of thing, is what I mean by that. So we can get some brilliant results and share them, and then we can turn some of those will then turn into bigger projects, and then I could like you do my own ideas. That will be amazing, and have some students to look after, which seems really like I want babies, but actually it's more like I want to make the research environment where people will thrive. Like I'd love to do it, like having done all, like I help with PhD students occasionally. I've done a bit of undergraduate teaching and stuff. I'm not like super experienced at any of that stuff, but like the bit I've done is like we could do this, like in some cases we could do this so much better for this student, and in some cases just like I want to be like you, supervisor. So like every student that I meet, I'm like teaches me something about how the relationship with students and supervisors works, and about their project, and it's like I just want to get into this exciting place, kind of thing.
Okay. Yeah, that sounds like a very nice summary of things to look forward to in the next 3 months, or even longer. I would say 3 months is just a number,
Yeah, I
especially
mean that
with
would take 3 months, but it will be like it could be the start of like, you know what I mean. Anyway, sorry, I interrupted you as well. That's
That's
really
fine.
rude.
I was just gonna say that I love the way you put it, you phrased it, that you want to create an environment where researchers can thrive. And it does sound like you want to have kids, but it's not the
No, I
kids.
don't.
But it is kids, these are science babies almost. Well, that sounds
Kinda.
wrong. That sounds so wrong.
Well.
Uh, but I understand what you mean, that you want to nurture the next generation of scientists.
Yeah, kinda.
That's what you want to do. That sounds amazing. So, Joe, this has been wonderful. But before we let you go, one
Okay.
last question for you, which is, what are the challenges faced by the field of materials or nanoscience, in your opinion, that the researchers are trying to work towards or trying to solve? What are the big questions?
Oh, okay. I should at this point say nobody read the comments on this because it's going to get awful from this bit, okay? Don't read below the line. I mean, that's a general rule on YouTube. But anyway, so there's a couple of things that are our biggest challenges. And they're not really, I mean, technical challenges are technical challenges, but you can solve them usually, like in terms of the science challenge. But in terms of I think it's more like the environment around us. So from my little narrow perspective of electron microscopy, I think we're going to have a bit of a research shock in the next year or so, or like a few years in the future, because at the moment it's really hard to train people to use electron microscopes. So grad students aren't learning it from scratch yet, because like you can't train them in the same room because of coronavirus, because you don't want to kill each other for the sake of learning how to use an electron microscope.
Yes.
Unless you can do some kind of virtual machine doing it from the next room thing, which not everyone can do, right? Not every institute has the resources to do that. So we're going to have a little skills gap in new postdocs being able to already do some electron microscopy, which is going to make life a bit tricky. Like there's going to be a lot more training needed once we, fingers crossed, have a vaccine and everyone can do face-to-face stuff again. Like there's going to be there's going to be a big load of training that's needed in like a bit extra training in if you want to have a new postdoc who can do electron microscopy. I mean, from a selfish perspective, there's more work for me to do, but that's the problem's bigger than me. Like I can't solve all of it, and like also I'm old and therefore expensive, kind of. And you know, postdoc people, you want to give postdocs to like people who just finished their PhD and can learn that as well. So like, you know, in big terms, like we're gonna have a bit of a skills kind of gap there, I think, which will sort itself out. It will just be kind of for a while. And this is where all the commenters with like flags in their username are gonna start saying mean things. So God, here we go. Let's take the plunge. So also in the UK, Brexit's gonna mess a lot of stuff up, because like we're just about to become estranged from a big funding body, and also it's going to make it a lot harder to collaborate with people in the EU, not just money wise. I mean, money wise it's going to be a massive loss, but like in terms of collaborating and being able to take samples around and that sort of stuff, and accessing funding that both parties can use and stuff, it's going to make life so hard. And so it's going to be very difficult to do a lot of the stuff that we were previously doing. I mean, it's going to take a lot more just headache and stuff. Not just headache, like a lot of projects won't happen that would have happened, which is going to be a massive shame. That will make a lot of people very sad. Not very sad, it will probably break careers as well. We're getting a lot of people are deciding they don't want to work here anymore. And are going to sort of, let me think of the destinations: Germany, Sweden, Canada, Ireland, lots of places that people have recently gone to because of Brexit, which means we lose those academics. Right. And some of our industrial partners will decide to leave as well, and that will make life tricky. And but also if there are shortages of food and fuel and electricity and stuff, like that's going to be the least of our problems. You know, we're going to be like, oh, we need some bread, kind of thing. Like, so yeah, I mean, but overall, like the people who are mean want to, no, not who are just mean. Like people who want to make a point about Brexit can probably stop listening and start writing their comments now. Okay, so generally, I think, in a global sense, it's everybody being sad and scared of everything. That's our biggest challenge. Like people just being too anxious to have ideas. I mean, like, how do you have ideas when you're wondering where your next meal's going to come from, whether your aunts are going to die of coronavirus? Like, to be honest, everybody being sad and scared is our biggest challenge. And also sort of kind of, I mean, I'm saying that as someone who like is least hit by coronavirus, like someone who's relatives and nurses and things are going to have that. I mean, it's not fair as well for so many people. Like, it's just, yeah.
Yeah, yeah, I understand.
Yeah, the state of the world is the biggest challenge. That's my summary, I guess.
Yeah, yeah, it's definitely going to affect the materials and nanoscience world as well. Challenges, external factors, external, like outside the field of materials and nanoscience, is what is going to affect the field itself, which is a bit. I wish it wasn't like that. But thank you for highlighting that, because we need to talk about this. We need to be prepared for what's coming, be it with the pandemic, be it with Brexit, be it with scientists moving out of UK, and then the funding and all that. All these things we need to talk about, acknowledge these things, these aspects, and then be prepared in whatever way we can. So thank you very much for putting it in words. And to finish on a different note, a more positive note, I myself learned a lot about your science, and I think it's super duper cool. And I hope
Thanks.
you get a ton of students that you can group, because I think they will learn a lot from you. So that
A ton of money, then I can get a ton of students. Yeah, I wish.
soon, at some point, it will grow slowly. It shouldn't happen right away, right? It should also grow gradually. So yeah, that would be amazing, and I hope you continue to do your amazing research. And looking forward to reading the POR paper for sure. And yeah, thank you very much for speaking with me. Looking forward to having you on Real Scientist Nano.
Thank you. Lovely to meet you.
Thank you for listening. To know more about us, please visit our website, realscientistsnano.org, and follow us on Twitter at realsci_nano.